episode of Coatings Decoded, otherwise known as the Paint People's Podcast. I'm your host, Jack Walker, and today we have a very special guest who is not only a specialist in mathematics, that's right, math, but is also my brother-in-law. Please welcome Dr. Bruce Rogers from Duke University onto the show. Bruce, how is it going?
Wonderful. Good morning. Thank you for having me.
Your sister is terrified.
Of course she is.
I recently had a coworker on an international flight, and that stewardess got over the intercom and asked if there was a doctor on the flight. Somebody raised their hand and tried to help, but a few seconds later, the stewardess asked if there was a medical doctor on the flight. Every time I hear this story, I think of you, Dr. Bruce.
Well, I am a professor of surgery.
Yeah. So that's a long story, but what's your doctorate actually in?
My doctorate is in applied mathematics.
And what is your specialty within applied mathematics?
I do stochastic processes, so how things change randomly in time, and uncertainty quantification, which is the study of error, how processes, measurements produce random results.
Awesome. That actually ties in perfectly with why I wanted to have you on the show. In real life, whenever I encounter questionable math, I tend to throw it at you. Would you say that is true?
That's true. It's mostly sports statistics.
Yes, because I am a sports junkie, but we like to dive deeper into the analytics side sometimes. Anyway, back to paint. Recently, we've had a competitor in our market space who shall remain unnamed trying to sow doubt into ASTM tests through variability. They're particularly focused on ASTM D4541, which is a pull-off strength adhesion test and is arguably the most widely used test in our industry. Their math was a bit off, so I wanted to get your take on it. As a mathematician and scientist, you know that these standards exist for a reason, and they're usually there to improve the repeatability and reproducibility of tests. Would you agree to that?
I would agree, right?
ASTM standards are crucial in our industry for ensuring a consensus test method is used to improve the variability or in this case, the repeatability and reproducibility of those tests.
I come from a manufacturing background. I used to work in medical manufacturing, medical device manufacturing, and the FDA was all over us all the time to make sure that we were producing things that wouldn't kill people.
Right.
And so produce standards so that you can follow the standards and make sure your product won't kill people. Or I guess in this case, make sure it adheres the way that you say it will.
The precision and bias statements help us understand the variability in our measurements. They provide a way to quantify how much our results might differ when the same test is repeated under different conditions. This is crucial for ensuring that our tests are reliable and that we can trust the results.
Well, yeah, so nothing is ever perfectly repeatable, right? So there's always going to be variability. And so if you want to know that you're sort of within process or doing something correctly, you have to have a measurement of this variation. Precision and bias together tell you how accurate your measurements are.
ASTM standards help us to compare our products with specific performance criteria. For instance, the ASTM D4541 is widely used test for measuring the pull-off strength of coatings. This test is essential for determining how well a coating adheres to a surface. But with 5 different methods available for this test, there's a lot of potential variability.
You're telling me that there's 5 different ways to measure the same thing? Then yeah, that's a lot of variability.
And that's why it's so important to specify which method is used when reporting results. Without this information, it's like comparing apples to oranges. The precision and bias statement help us make sense of these differences and ensure that we're making accurate comparisons. I cannot stress this enough that when you're looking at results for this test, that you need to be looking at the same method. If you're given an ASTM D4541 pull-off result and you're not given what method was used to determine that result, it's not useful because you need to really be able to compare apples to apples and oranges to oranges.
That's why we do math.
Simplifying the math. That's why I called you, as I mentioned earlier. The standard gives us repeatability and reproducibility from the world of statistics. Could you explain these concepts?
Sure. Well, repeatability is when the same person is using the same things and using the same instruments and making the same measurement over and over. So, like I said, if you were to take your thermometer outside and then read the number, and then go back outside 3 minutes later and read the number again, that would be repeatability. You're using the same instrument, the same person, the same environment. Now, reproducibility is when a different person in a different lab is using a different thermometer. I think important to us, like, is you can't have reproducibility without repeatability.
Right.
And the reproducibility of the result is what's important. I'm in North Carolina, and if I want to do the experiment, I want to make sure that I can compare it to results that you've also done in Missouri.
Right.
And that's what the reproducibility standards are for.
These standards help us understand how accurate a test is from lab to lab, place to place. Some tests are also performed in the field. So there's a lab to field factor as well. All are part of the reproducibility factor of the standards. The consensus ASTM tests validate products and their performance before release. They ensure proper adhesion during the application and validate life expectancies. So the fact that our competitors decided to pick on the variability here, but specifically the reproducibility limit on these standards, is bizarre. Specifically picking on ASTM D4541, a standard that's used by everybody all along the coding process, is actually really mind-boggling to me. Additionally, they picked on the reproducibility limit for one method and applied it across the entire standard.
Do the different methods use different instruments?
Yes, the different methods use different instruments, making it important to compare the results accurately, apples to apples.
And it doesn't make a lot of sense to pool the results.
Again, engineers and specifiers must ensure they are comparing apples to apples. The competitors claim that ASTM D4541 carries a 76% variability is misleading. First, method B carries a 76% reproducibility limit, which isn't the same as variability, and it's the largest reproducibility limit allowed by the standard. All the other methods carry a much tighter reproducibility limit. Bruce, would you say the standard states a 76% variability for all methods?
It's telling me the exact opposite of that. Method E has a 34% reproducibility limit.
Which is really good.
Yeah.
The competitor really kind of took it a step further and mentioned that because of this variability, one, again, we're using peanut butter, we're spreading it across the entire standard, which we've established is not the correct way.
Exactly.
But because of this variability, the competitor said that you can say results of 500 PSI and 2000 PSI are basically the same. After evaluating the statements in the standards and based on your mathematical specialty, would you agree that results differing of 1500 PSI are basically the same?
No, I would say that those are not the same from a process standpoint. A measurement that is center and a measurement that is way on the tail next to your outer limit of your process, your 99th percentile, that should raise a red flag.
In fact, not only are they not equal, but for every other method in the standard outside of method B, the data set of 500 PSI and 2000 PSI would be considered suspect. Let me say that again. Not only is the data set of 500 and 2000 PSI not equaled, but it is considered suspect by 4 out of the 5 acceptable testing methods within ASTM D4541. Again, the 76% reproducibility applies only to one method within, not the entire standard. Is it fair to apply its reproducibility across all results obtained by this test method?
No, not even a little bit, right? So we can't pool these results. You have to keep your you have to keep your instruments the same. Follow the standards and the instructions.
Understanding that the reproducibility number from one method cannot be applied across the entire standard is crucial. This standard allows for more precision and consistency from lab to lab with the other available methods. Method B with the lowest reproducibility is hardly ever used in labs and is not the method that coding suppliers are providing in a performance data summary to engineers and specifiers. It's simply not. Method B not only carries the lowest reproducibility, but also is the process that produces the lowest testing results when compared to other methods. With most of it, if not all of methods B use coming from the field, it is naturally lower results are often overshadowed by laboratory results using a more consistent method. I believe this known difference is what our competitors are using to make outrageous claims of performance equality. With all that, thank you, Bruce, for breaking down this complex topic for us. It's clear that ASTM precision and bias statements play a crucial role in reducing variability and ensuring the reliability of our tests.
My pleasure, Jack. Thank you for having me. Anytime that you want to talk standards, give me a call.
And thank you to our listeners for tuning in to this episode of Coding's Decoded. We hope you found this discussion on ASTM precision and bias statements informative and helpful. Stay tuned for more insights into the world of codings and testing standards. Until next time, keep learning and stay curious.